Hey everyone, welcome back to another lesson. I am so sorry for the delay since the last time I got a chance to upload. We've had some technical issues and a pileup of schoolwork and just so many things going on, but hopefully things will be back on track beyond this point. So in this lesson, I'm going to discuss some of the foundational concepts that we're going to need in our geometry unit. So today we're going to be covering the properties of simple shapes. Now I realized the last time I uploaded this there were some audio issues, so I'm going to hope that there are no issues this time. And I also, if I'm remembering correctly, the last time I tried uploading this, the lesson was exceptionally long. So hopefully I'll be able to streamline some of the concepts and not really over-explain things so much this time. I do try to explain the concepts in a little bit more detail than is necessary, just in case there's any doubt or any questions that you may have. I'd like those to all be cleared up as quickly as possible in the first lesson or two of the unit, just because those concepts end up being important later on in the unit. So I tend to over-explain things in the earlier lessons, so if you are getting bored by some of this, know that I'm just trying to make sure that all my bases are covered. But without further ado, let's get started. So today we'll just be looking at some simple properties of the following shapes. So we're going to start off this unit by just looking at, some of what are the qualities that make a square, for example. So really simple stuff to kick off this unit, because this is our first real math unit of the year. It's just coming later than it should be, that's all. But yeah, so we're going to start off by looking at the properties of these simple shapes like squares and triangles and circles, and after that we'll extend this to slightly more complex shapes. So maybe we can, for instance, let me just get my pen here. Maybe for instance we can talk about how you might calculate like the area contained within a shape that's like a rectangle attached to a semicircle or something. So, if you've got a semicircle here and a rectangle here, how might you calculate the area of such an object? So we'll talk about things like that later on in the unit. But for now, we will be focusing mainly on just these sort of simple properties, the things that make these shapes the shapes that they are. So let's get right into it. Now you may have seen in previous math classes, or in just in pictures online, if you've ever seen any memes perhaps of geometry, and if this is your first exposure to these kinds of diagrams, a very natural first question, and maybe a basic question that hopefully you all know the answer to, but if not, very basic question is, what do all the tick marks mean? We've got a whole bunch of shapes on the screen here, but we've got a bunch of lines and arcs and like these part circles and stuff here. These are arcs, and like pairs of lines here, and then a single line here, pair of lines there, a vertical line that's inside the shape. All of these different symbols. What do they mean, and why are they important when we're talking about these shapes? So in this lesson, that's basically going to be the main topic of what we cover. Is when we look at all these shapes, we're going to explore what these signs mean and why they're important. So one thing that's not immediately obvious when people are first exposed to a subject like anything in geometry is the fact that we can talk about shapes in more ways than we might think when we first see them. So for example, if you ask somebody to draw a triangle, they'll draw something like this, and yeah, that's a triangle. Most people shouldn't argue with that. But we can talk about triangles in a whole bunch of different ways, and you can see some of those different ways on the screen. Right in front of you are 6 different classifications of triangles, and 3 of them are based on the side lengths of the triangle, and 3 of them are based on the angles within the triangle. So let's break this down. I'm going to get rid of the triangle over on the side here, and let's break this down. So when we're looking at classifying a triangle, so basically describing a triangle by side, what that means is looking at how many sides of the triangle have the same length as another side or as the other 2 sides. So, for example, if we're looking at this first example here, this is what we call an equilateral triangle. Now, what is an equilateral triangle? Well, we've got a description right here. It says an equilateral triangle is a triangle that has 3 equal sides, so 3 sides that are equal in length, and all the angles on the inside of the triangle right here, so that's this angle, and this angle, are all 60 degrees. Now, hopefully you guys remember that, you know, if you've got, let's say if I draw something like this and like this, that this angle in here is 90 degrees, but the angle going all the way over to the other side is 180 degrees, and the angle that goes all the way around and comes back to the beginning is 360 degrees. So basically, if you take something and you rotate it or you spin it, right? If you take an object and you spin it by some amount, by some, you know, by some angle, then it'll take 360 degrees of rotation to bring it back to where it started. So in the case of an equilateral triangle, looking at this diagram, that's this very crude diagram that I've drawn in here, we can envision that a 60-degree angle should look something like this. Something like that. It's not perfectly drawn, but we can imagine that a 60-degree angle would look something like this. And if you look at the equilateral triangle, that's not too bad, right? That looks similar-ish to what I've drawn here. Obviously, it's not perfect because I'm drawing it with the mouse on the computer, but it's not that far off from what I've drawn. And honestly, this is the correct one. This is what a 60-degree angle should look like. And then you can see that the other angles look to be pretty much the same size as well. So in the case of an equilateral triangle, all 3 sides are exactly the same length, and all the angles are exactly the same as each other, and they're all 60 degrees. One important thing to remember about a triangle is that if you add up the measurements of the angles that are on the inside of the triangle, so these 3 angles here, if you add all those up, it'll always be 180 degrees. So if you think about that, then this fact of all the angles being 60 degrees is pretty obvious. If all the angles have to add up to 180 degrees on the inside of the triangle, and you have 3 angles that are all the same size, then they all have to be 60 degrees, because that's just 180 degrees divided by 3. So that's how we can define an equilateral triangle. Now, this doesn't answer what the tick marks mean. So let's explain that really briefly so that we can use it to describe the rest of our shapes. Basically, what the tick marks mean, and it doesn't matter how many tick marks there are. All that matters is that you have the same number of tick marks on one side as the other side that you wish to sort of compare it to. And what the tick marks mean is that, so in the case of what I've drawn here, this side, which I've got 2 tick marks going through, and this side, which also has 2 tick marks going through it, are the same length. That's what the tick marks mean. And I could have done this with 1 tick mark, like this. This is the same thing. All 3 sides, all the sides that have that same number of tick marks, so in this case 1 tick mark, in the little picture I've drawn on the left, those are all the same size. That's what I'm indicating with the one tick mark going through it. And basically the reason for it is, as you can see when I'm drawing it on the screen myself, it's not perfect. They're not all perfectly straight lines that I've drawn. The angles aren't all going to be exactly 60 degrees when I just draw it by hand. And the sides are probably not all the same length. So if I want to communicate to you that all the sides are supposed to be the same length, even though I haven't drawn them perfectly, then I'll just stick those tick marks through it to indicate that these sides are supposed to be the same length as each other. And again, I could do this with one tick mark, I could do it with two tick marks if I wanted to, I could do it with three tick marks if I wanted to. It doesn't matter, as long as the number of tick marks that I have for each side is the same, then all the sides with that same number of tick marks are the same length. That's what that's trying to communicate. And maybe that's a little confusing the way I've described it. Hopefully not, but if it is, then we can look at this next case to try and understand it a little bit better. So the next case is when instead of having all three sides being equal, now we've got two sides that are equal in length. And so what happens here is, if you look at the diagram that we've got on the screen, what this is saying is that this side and this side are the same length as one another, but not the same length as this last one on the left. And so the way you could do that, you could draw it a few different ways, right? Is if I want to communicate to you that in this triangle that I've just drawn, that this side here and this side here are the same length, I could put a single tick mark through both of those and just nothing through the last one. Or I could put a different number of tick marks through the last one to show that it's a different length from these two, and no, I didn't just forget to put a tick mark through that side. Or if I prefer, I could put like one tick mark through the side that's different and two tick marks through the rest of them, or no tick marks, or whatever. All that matters is that only this side and this side have the same number of tick marks as each other. That tells us that these two sides are equal in length. And then this side, it could have no tick marks, or it could have three tick marks, or whatever. As long as it's a different number from the number that we've got here, the number of ticks that we've got on each of these sides. If it's a different number of tick marks here, 0, 1, 3 in this case, that just tells us that this side has a different length. So that's all that we need for that. One additional point that we can talk about when we're looking at equilateral triangles and isosceles triangles, so these first two cases here and here, is if you want to show that the angles, that any two angles are the same. So if I've got a triangle that looks like this, and I want to say that the angle inside here and the angle inside here are the same, even though I've drawn it poorly, then I can just draw in like an arc here and the same arc here. So in the case of the equilateral triangle, drawing in those arcs could be communicating that, so like drawing in this arc here and this arc here and this arc here, could be communicating that all those angles are the same. Another thing you might see is instead of one arc to have two arcs. So maybe I'll do the two arc example here. So in the case of the isosceles triangle, these two angles are always equal to each other, and this last angle is going to be different. So what we can see here is that the isosceles triangle is the one which has two sides that are equal, and so we've got the tick marks on two of the sides, so those are the two sides that are equal, and two equal angles. So those are these two angles out here, that if you think of the, so like if you turn your head to the left and you see the two equal sides making like a V, then the equal angles are the ones that aren't in the little corner of the V. All right, so so hopefully that that makes sense. So so that's it for the equilateral triangle and for the isosceles triangle. Now let's move on to the scalene triangle. And so this last one here this is the case where none of the sides are equal in length and none of the angles are equal either. And so this basically, you don't need to make any tick marks. Not making any of the tick marks and not drawing in any of the arcs for the angles just means that there are no equal sides and there are no equal angles. Alternatively, if you wanted to make it really clear that they're all different lengths, you could put in like 1 tick mark here and 2 tick marks here and 3 tick marks here. I've drawn that really poorly, but hopefully you get the idea. 3 tick marks here to indicate that all 3 sides have different lengths. And you could do the same thing with the angles. I could put in, 1 arc here and 2 arcs here and 3 arcs here to show that the angles are also all different from each other. So that's the last way that we classify the triangles, by how many sides and angles are equal to each other. That's this case over here. And then the other way that we can classify triangles is based on the type of angle or angles that we see inside the triangle. So we can see in this first one, we can classify a triangle as a right triangle if one of the angles inside is equal to 90 degrees. And that's what this square, thing in the corner, that's what that's trying to communicate, is that this angle down here is 90 degrees. Now, of course, if the total number, if the total of the 3 angles needs to be 180 degrees, like we established earlier, then obviously you're not going to have more than one 90-degree angle, because then you don't have any degrees left over for the third angle, right? You've got 3 angles in the triangle. If 2 of them are 90, that already adds up to 180. So your last one would have to be 0. A triangle that has 2 90-degree angles, no, that's not going to work. Yeah, so basically, if we have a right triangle, that's one which has a single right angle somewhere in the triangle. Then we could also call this type of triangle, well, we've got a different way that we can classify triangles by angle, and that is the acute triangle. And so that's one where all the angles are acute angles. Now remember that acute angles are all the ones that are less than 90 degrees. So if I draw this kind of thing again, and I say that this right here is 90 degrees, if I say that I'm starting from 0 degrees over here, then everything in here, every angle in here is an acute angle. So if this, whoops, that's drawn horribly. If this, let's say, is my 90-degree angle, then making an angle that's like this would be an acute angle, and like this would be an acute angle. Anything that's a smaller angle than 90 degrees is an acute angle. And so you can have a triangle where all 3 of the angles are less than 90 degrees. So this one in here is less than 90 degrees, this one here is less than 90, and this one here is less than 90. And if you have all 3 of them less than 90 degrees, you have an acute triangle. And then the last one is an obtuse triangle, and that's one where one of the angles is bigger than 90 degrees, which is, in this case, this angle right here is bigger than 90 degrees. So in the drawing over here on the side, all of these angles here would be obtuse angles. So an angle like this would be an obtuse angle. An angle like that, right in there, that angle would be an obtuse angle because it's bigger than 90 degrees, but smaller than 180. So that's what an obtuse angle is, and we use it to define what an obtuse triangle is. So you can talk about triangles in a few different ways. Now, obviously, you can't have an equilateral triangle that's also a right triangle, because in an equilateral triangle, all the angles need to be 60 degrees. And for a right triangle, you need the angle, one of the angles to not be 60 degrees. And same for the obtuse triangle, you need one of the angles to be bigger than 90. So basically what we have here is that for every equilateral triangle that you have, it has to be an acute angle, an acute triangle as well, because all the angles have to be smaller than 90, and the equilateral triangle satisfies that, and it doesn't meet the criteria for being a right triangle or for being an obtuse triangle. So all equilateral triangles are also a type of acute triangle, but you could have like an obtuse isosceles triangle or an acute isosceles triangle or a right isosceles triangle. In fact, it looks to me like this triangle down here is an obtuse isosceles. We would be clear about that if they'd marked the side lengths as this one and this one. If they said that those two are equal, then we could say this is an obtuse isosceles triangle, because then we know that the two sides are the same length. And this one up here looks like a right isosceles triangle if these two sides have the same length as each other. Now, they haven't specified that for us, so we don't know for sure, but by looking at it, it does appear to be that that's the case. So that's about it for the triangles part, so let's move on to something different. So now let's let's start by talking about the tick marks here, but we've already talked about some of these things on the previous slide with the triangles already, but there is one part of it that we've sort of left out up until this point, which is whatever's going on up here. So we've already talked about the rest of it, so let's go over that really quickly and just talk about the rest of it. So if you've got lines with these tick marks through them as a part of a shape, or just as lines like they're shown here, that they're not making any triangles or squares or anything like that, lines that have the same number of tick marks, what that's communicating is that they're the same length as each other, even if they don't look like it. Like if you asked me, is the line AB, this line segment here, that's what we call it, is a line segment if it has two endpoints. A line, on the other hand, would extend all the way to infinity in both directions, but a line segment has an endpoint here, and we name the line segment by the labels that we give to those 2 points. So this one is line segment AB, or BA is the same thing. So the line segment AB, it's got these 2 tick marks through it, and we've got the line segment CD here, which has 2 tick marks through it. So what this is telling us is that AB and CD are the same length as one another, even if one maybe looks longer than the other. And then the same deal with EF, line segment EF, and line segment GH that we see here. They've got 1 tick mark through them, which tells us that they're the same length as each other, but a different length from everything else. And just as a quick side note, if you wanted to write line segment AB and indicate that you're talking about a line segment, then you can write AB and put this bar over both letters. That indicates that you're talking about a line segment. And it's the same thing if you wrote BA. When we're talking about line segments, it doesn't matter what order you write that in. So you could have BA. It means the same thing. Now let's move on to a discussion of the angles over here. I did say on the previous slide that putting an arc through an angle like this might indicate that it's the same angle as, another angle over here, if I put an arc through that. But we put a single arc through angles just to point out that there's an angle there. So to point out for sure that we mean that they're equal, you can see that there's this little additional tick mark going through it. So maybe this and this would be a better way to represent that those 2 angles are equal. And alternatively, we talked as well on the previous slide about how you could just put more arcs. So instead of 1 arc for the angle, you put 2, and you put 2 for the other one. That's communicating that those angles are the same as each other. Then of course we've got the right angle up here, which is represented by basically making a mini square in the corner of the angle. And this is a unique enough symbol that you don't actually need to write 90 degrees. So if I draw any angle, whoops, that's my mouse not drawing the whole line properly. But if I draw something like this, and I want to say that's a right angle, I can just make this little square in the corner, and I don't need to write 90 degrees. That square is communicating that it's a 90-degree angle. So that covers all of those points. Now let's move on to this business with these arrows going through the lines. What that's telling us, what those arrows are telling us is, so similar to with the tick marks here, is that if you've got one arrow going through this line and one arrow going through this line, that is telling us that they are parallel to one another, meaning they're pointing in exactly the same direction. They're never going to touch no matter how far you extend these lines in the direction that they're pointing. So like I could extend this line and I could extend this line, and no matter how long I keep doing that, they are never going to touch, provided that I keep the lines pointing in the same direction. So it follows the same kind of rules as these guys down here with the tick marks, in that if I've got one arrow, maybe the arrow is not super clear, so you might often see it with, like, if it's hand drawn, the arrows might look bigger like that. But you can see in any case that we've got one tick mark going through these two green ones, and then, sorry, not tick mark, one arrow going through these green ones, and then two arrows going through these orange-ish ones, and then three arrows going through these blue ones. And so following the same kind of logic as with the tick marks, the same number of arrows means that all lines with that same number of arrows are parallel to each other, but not necessarily parallel to everything else. So these two blue lines, they've got the same number of tick marks, so they're parallel to each other, but they're not parallel to the orange ones, and they're not parallel to the green ones, because the tick marks are, or the arrows are different. So hopefully that clears up most of the concerns that you may have about these tick marks. So now let's dive into using these tick marks when we look at some other shapes. I realize that this lesson is already almost half an hour long, so let's see if we can not take ages to get through the rest of it. So now we get to talking about some sort of easy properties. Now with triangles, we saw that there are a bunch of different ways that we can classify them. We've got acute equilateral triangles, and we've got right isosceles triangles. Squares are easier. Squares are squares. They've got a few properties that they have to have in order to be a square, and those are these properties that are written here. If you meet all those criteria, you have a square. So what I'm going to do is I'm going to draw my own little square-like shape down here. That's already awful. Let's try that again. So if I try to draw something like this, now I've drawn it slightly badly and kind of on purpose. So it's not obvious right now that this shape here meets all of these criteria. The sides don't look like they're all the same length. The angles certainly don't look like they're all 90 degrees. And we don't know if opposite sides are parallel. So by opposite sides, I mean like this side and this side, or this side and this side. That's what the opposite sides bit means. So if we look at this square over here, we can use the tick marks and the symbols that we just studied to help us out. What are the criteria of a square? The first criterion is that all the sides have to be equal in length. Well, how do we communicate that? We communicate that with the tick marks. Equal length, we use the tick marks. So we can see that all four sides have the same number of tick marks. It could be one, it could be two, so let me do it with two over here. If I put two tick marks through this, and two tick marks through this, and two tick marks through this, and two tick marks through this, whoops, then that's telling us that even though I've drawn the shape poorly, I meant it to be drawn in such a way that all four sides are equal in length. So that's this first point taken care of. Let's put a check mark there. The second point, all the angles are 90 degrees. How do we represent 90 degrees? With the little squares in the corners of the angles. So I can go ahead and do that. I can put in the little square here, and the little square here, and the little square here, and the little square here. Now again, I'm not drawing this perfectly, but I'm trying to draw it with a mouse on the computer, so it is a little harder. But if you're careful with it, then it'll look honestly fairly similar to this guy over here. So all sides are equal in length. We already took care of that. All angles are 90 degrees. We've just taken care of that by marking in the little squares to indicate that even if it doesn't look like it's 90 degrees, I meant for it to be 90 degrees. So that point is taken care of as well. Last one, opposite sides are parallel. Now remember, for parallel, we need to use the arrows. I don't know why my mouse keeps doing that. We need to use the arrows to indicate that two lines are parallel to each other. So by opposite sides, we mean like the top and the bottom are parallel to each other, and the left and the right are parallel to each other. So I can indicate that with tick marks, or not tick marks, excuse me, with arrows. And so the top and bottom need to be parallel to each other. So I can put, let's say, one tick mark here. Oh my goodness, one arrow here and one arrow here for each case. And then the left and right, this side and this side are are parallel to each other. Excuse me, it's been a long day. The left side and the right side are parallel to each other. So I can indicate that with arrows as well, but they need to be a different number of arrows than we have here, because we've already used up one arrow to mean parallel sort of in this direction. So I'll use two arrows. So that'll look something like this. So two arrows here and then two arrows here. And by doing that, I have indicated all of these necessary points to show that what I have drawn is indeed a square, because all of those statements are true. All the sides are equal in length, all the angles are 90 degrees, and opposite sides are parallel. Now you might be wondering, well, if opposite sides have to be parallel, why don't we have the tick marks on this square here? And the reason for that is the four angles all being equal to 90 degrees takes care of the parallel business by itself. So we could, if we wanted to be absolutely sure, we can absolutely go ahead and add in those arrows for them being parallel. But the way the angles work out, with all the angles being 90 degrees, the parallel nature of the opposite sides is built in, is built into the structure of the shape, just because of all the angles being 90 degrees. But anyway, that's that for the square, so let's move on. Next up is the rectangle, and this is very similar to the square. So let's examine this by drawing another shape here that's rectangle-esque, and we want to show that it is actually, I've tried to draw a rectangle and not something else. So the first point, opposite sides are equal in length. Opposite sides, again, that means like the top and the bottom are equal in length, and the left and the right are equal in length to each other. So in the shape I've drawn, it doesn't look like that's true. So if I want to communicate to you that the top and bottom are equal in length, I'll put a tick mark through the top, I'll put a tick mark through the bottom. That tells us that the top and bottom are supposed to be equal in length. As for the left and right, again, it doesn't look like they're the same length, so I'll put two tick marks here and two tick marks here. I could have done two tick marks through the top and bottom and one tick mark on the left and right. It doesn't matter. All that matters is that the top and bottom have the same number of ticks, and the left and right have the same number of ticks. The actual number of tick marks doesn't matter. It just matters that you have the same ones here and here, and the same ones here and here. So that takes care of the opposite sides being equal in length. The second part is all the angles have to be 90 degrees. So just like with the square, we can mark in the four angles like this. And there we go. Now we've communicated that all the angles are supposed to be 90 degrees. So that's this point taken care of as well. The last one is that opposite sides need to be parallel. And now once again, with all four angles being 90 degrees, that's actually taken care of for us. But if we want to be specific and explain clearly that this side is parallel to this one, then we can add in the arrows for them being parallel, and then we can do the same thing here and here, with a different number of the little arrows to indicate that they're parallel but in a different direction. So there we go. That's as easy as it can get for the rectangle. Let's move on. The next one is the rhombus, and this is an interesting shape. It's quite similar to the square in the sense that, well, we've got all the sides have to be the same length, just like a square, and opposite sides need to be parallel, just like a square, but the angles don't have to be 90 degrees. So what we can see here is that they've tried to show that like it's almost like you take basically a rectangle. It's actually not it's not a square that they've started with. They've started with basically a rectangle, and then just sort of shifted the bottom side over a little bit. So basically, if you start off with something that looks like this, if you take this bottom side and you just scooch it over to the side a little bit, and you keep the top and the bottom the same length, at some point you'll get to a point where all the four sides are the same length. This one and this one are parallel. This one and this one are parallel. All of them are the same length, but the angles aren't all 90 degrees. So that's basically, those are the requirements for the rhombus. All the sides are equal in length. The angles do not have to be 90 degrees, so you could indicate which angles are the same as each other. So for example, on this diagram here, this angle and this angle are the same. So maybe I'll put 2 arcs there to show that they're the same. And then for this other one, I'll put 3 arcs, that this one and this one are the same. So that's how we can communicate that the angles are the same as each other but different from other ones. Now obviously this can get a little bit messy. With the lines going through here, it's hard to draw the angles that are just one arc with a tick mark, because the tick mark would kind of be covered up by these lines going through it. So I went for 2 arcs and 3 arcs, but you could do something simpler if you prefer. But there you go, that's a rhombus, and we can be sure that the 4 sides are the same length by drawing the single tick mark through them, and we can see that here as well. Tick, 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 tick. And if we want to indicate the parallel nature of those lines, we can do the same thing as well. We can draw arrows here, and then a different number of arrows here and here. So there we go. That's it for the rhombus. Next up is the parallelogram. Now this one is similar, the same way that a rhombus is similar to a square, the parallelogram is similar to a rectangle. So opposite sides are equal in length, just like a rectangle. And so we can see that I've got a few different diagrams here just because they sort of show things in a couple different ways. The way that this website has chosen to represent equal length is they've done the tick marks, but they've also color coded it differently, that the sides that are the same length as each other are actually colored differently. So that's a neat way to go about it if you feel like it. But the standard way is with the tick marks, and you can see they've included the tick marks as well, that the line segment up here, AB, is equal to DC, or CD if you prefer. And they've put the tick marks there to indicate that. Meanwhile, these two down the sides, so AD and BC, are the same length as each other, and they've each got the 1 tick mark going through them. Just like the rhombus, the angles don't have to be 90 degrees. So once again, you could indicate that with, for instance, an arc and a tick here, an arc and a tick here, to say that those 2 angles are equal to each other, but they're not equal to this angle here and this angle here. So for example, you could draw in the tick marks like that. In the case of the rhombus and the parallelogram, the opposite angles, so the ones that are, across from each other, these angles will be equal and these angles will be equal, and that's taken care of through the fact that the opposite sides are parallel to one another. So with the parallelogram down here, they haven't indicated that the angles are all the same, but they've indicated that the top side and the bottom side are parallel to each other, and they've indicated that the left side and the right side are parallel to each other. And we can see just another example here. Again, they've color-coded the angles differently, and it also, when you're drawing the arrows for whether they're parallel or not, it doesn't matter which direction you go in. You can see this one is going from D towards A, it looks like, with the way that arrow is pointing, and then this one looks like it's going from B to A, pointed in the opposite direction. They've even labeled them all differently. So you have freedom to label the points the way you want, and then you can draw the arrows in whatever direction you want as well. So that's all up to you to label them and draw the arrows in how you want. All that you need to make sure that you do is draw in those arrows appropriately to indicate which sides are parallel to each other. Next up is the trapezoid, and this is fairly simple. We're not going to work too much with trapezoids, maybe a little bit here and there, just as a curveball. But basically, trapezoids only have one pair of opposite sides that need to be parallel. So basically, the top and bottom. In this case, we can see the top side and the bottom side are parallel to each other, but the left and right are not. And they've indicated that by not drawing any arrows through them. And then this one over here, we've got, again, the top side and the bottom side are parallel to each other, but the left side and the right side are not parallel to each other. Now we've got two different types of trapezoids here. We've got the non-isosceles trapezoid, where this side and this side have different lengths, so they should have a different number of tick marks. And then we've got the isosceles trapezoid over here, where they are the same length, and so they should have the same number of tick marks. The parallel sides don't have to be the same length as one another. This is basically the only criterion that you need to meet, that and the fact that it's a four-sided shape. Because we're mostly, aside from the triangles and circles and whatnot, we're mostly going to be concerned with four-sided shapes, or quadrilaterals. But yeah, so that's it for the trapezoids. I'm not going to delve into too much detail because we're not going to be working with them all that frequently, but there you go. And here we are. I just mentioned triangles on the previous slide. Here are triangles again. We've already seen them before, and we discussed this in detail, but here's the picture again, maybe slightly larger than it was before. In case you want to just note down quickly that triangles can be characterized by their sides, or they can be characterized by their angles. So characterizing them by sides basically means describing the triangle based on how many sides are equal in length. And also we know that from earlier that the number of sides that are equal in length also tells us the number of angles that are equal in length. So either it's all three of them are equal, or two of them are equal, or none of them are equal. Because it doesn't mean anything to say one of them is equal, right? Equal to what? Equal to nothing. That means none of them are equal. So anyway, we can describe triangles in a few different ways when we look at their side lengths or by their angles. We've already discussed this way back at the beginning, so I'm not going to get into it again, but here is the slide again in case you want to copy anything down or just test your memory from all the stuff we saw at the beginning with the tick marks and the angles. So I don't have very much to comment on here. You guys can pause the video, or when you get home you can go back to this point in the video about 44 minutes in. If you want to note that down in your notebooks, about 44 minutes in. This is just a table from the internet that shows the different shapes. We're not worried about this last one at the bottom, the kite. Do not worry about this one. We're not going to be working with it. If we are, I will tell you, but as of right now, I do not plan to work very much with the kite. But for the rest of the shapes, you can see basically the same descriptions that I gave you, but just sort of all in one place. A little picture, the name of the shape, and a description of of what, what makes that shape the shape that it is. And you can also see, interestingly, in these descriptions, how the shapes are related to each other. So we've got a parallelogram, which we saw. The opposite sides are equal, the opposite sides are parallel, and the angles don't have to be 90 degrees. And then we can see that a rhombus is just a special kind of parallelogram where all the sides happen to be equal in length, because the rest of the criteria are met. The opposite sides are equal, because they're all equal. The opposite sides are parallel. That's true for a rhombus. And not all the angles are 90 degrees. That's fine. Similarly, a rectangle is also like a special kind of parallelogram. It's just got all right angles because the other criteria are met. The opposite sides are equal in length. The opposite sides are parallel. And in the case of a rectangle, all the angles happen to be 90 degrees. And so then we come to the square, and we see that a square is basically a very special type of parallelogram, right? Because the opposite sides are equal, because they're all equal. The opposite sides are parallel, and all the angles happen to be 90 degrees. They didn't have to for the parallelogram, but they could be. So a square is really a special type of parallelogram, or a special type of a rhombus, or a special type of a rectangle. In fact, it's all of those things at the same time, and it's just this special shape that's got these nice properties of everything is the same. It's like the four-sided version of the equilateral triangle, where everything is as equal as it can be. And so we gave it a special name. We call it the square, but it's really, if you think about it, it's a special version of a parallelogram. And then here we go. Here's another similar table that you can make use of. Again, once again, we do not need the kite. But for the rest of them, these have basically the descriptions that are similar to the ones that I showed you earlier in the lesson. I'm not going to test you on the descriptions that are given here, because some of them are a little different, like this one about diagonals bisecting each other at right angles. I'm not going to ask you about that stuff. But just if you want to see all of that information collected in one place, this is also a table from the internet. It's got the names of the different shapes, a little picture of each one, and the descriptions of their properties. So that's honestly basically it. There's just a couple of fun tidbits of information I wanted to throw in at the end of the lesson. There's a really fun game if you want to play around with geometry that lets you make shapes that, constructions that look like this or like this. What's going on here is that if you just use a bunch of straight lines and circles, you can generate shapes like this pentagon right in there. Or, you could do it for a whole bunch of different things. Over here, you've got, this looks like what we've got here is that this angle right in here and this angle right in here are exactly 30 degrees. And so that means that this whole angle right here is precisely 60 degrees. So if you want to play around with geometry, it'll ask you questions where basically you take a bunch of circles and lines and it says make a 60-degree angle that's always going to be 60 degrees. No matter how big you make the circles or how long you make the lines, it'll always be a 60-degree angle, and you can play around with those shapes. The app is called Euclidia. I will write that on the screen for you. This is not sponsored or anything, it's just a fun game. Euclidia. That's a U. That second letter is a U, that last letter is an A. Euclidia. So yeah, so if you want to play around with geometry, you can do that. The shape on the right, it's not from the game, but it's just an example of, if you draw a bunch of lines and circles, you can get other shapes out of it that maybe you didn't expect to see, like a perfect regular pentagon, for example. There's also some fun with the flag of Nepal. It's in the constitution of Nepal how to mathematically make their flag. The way their flag is supposed to actually look is on the right, and all the mathematical work that goes into constructing the flag is shown on the left here. So if you go on YouTube and you look up Nepal flag math or something, then you'll find a great video by Numberphile that goes through making Nepal's flag, like mathematically perfectly. So there's just some fun for you. And of course, where would we be if I wasn't keen to scare you at the end of every lesson just a little bit? This isn't anything you guys need to study. This is stuff related to the beginnings of my general relativity course that I took last winter. Um, but basically, I'm just hinting to you that geometry and just exploring geometry in general can take you very far and to unexpected conclusions. So if that's something that you're interested in pursuing, know that things get a lot more interesting than just the properties of simple shapes. But that's all that I've got for you guys today. Simple shapes are all that we're covering in this video. I think this has ended up being shorter than the last time I recorded it, but that means that I might have left out some details or gone a little bit too quickly. So if that was the case, let me know. And if not, then I will see you all in the next video. Hopefully in a few days for real this time. Have a good one.